Thank you for the invitation of Professor Li Tak to give the chance to give my presentation here. And as the coronavirus 19 is very serious, I hope you guys are safe in your country. So today I would like to give a presentation about energy harvesting from flow-induced vibrations. I'm Junlei Wang. I'm working in ZhengZhou University in China, and now I'm as a visiting scholar at the University of Auckland. So today I would like to introduce my presentation into the these parts. Firstly, I would like to introduce some background to energy harvesting, and then I want to introduce classifications of FIVEH, and then I will comprehensively introduce vortex-induced vibrations. And first, I will introduce an important part to solve this problem, that is the computational fluid dynamics. And the fifth part, the galloping energy harvesters. I believe some audience will be very familiar with that. And at last, I want to introduce some existing challenges and conclude something about energy harvesting from flow-induced vibrations in my personal point of view. Okay, so as everyone knows, nowadays, wireless sensor networks has been developed and utilized in most engineering regions and people's normal life. For example, we want to monitor the signals reflected from factory, on the forest, plane, in the city, on the transport, and the military, the hospital, at home, or outside sports. So then we can get some signals by the sensors, which can transfer back to IP networks. Then we can monitor the informations. Unfortunately, it is quite hard to power these sensors because there are large amounts of sensors distributed everywhere. And thus, we need to power these sensors continuously and better to frequent changes the batteries. Fortunately, nowadays, we have some new technologies, for example, energy harvesting. So they can be used to power these such low power grid equipments. So energy harvesting is a kind of low power grid, sustainable, and which does not need to change the batteries. So it is a quite good way of powering the wireless sensor networks. Generally speaking, energy harvesting has the following ways. For example, solar waves, from tide, from vibrations, from wind, thermal, or radio frequencies. So let's summarize what is energy harvesting. Energy harvesting is a low power, continuous, and no battery changes needed. Okay. But among these types of energy sources, I think wind energy or flow energy is very good because it is not constant for the weather. However, for wind energy, some traditional hydro generators, the size is usually to be designed very big, as you can see, because it is based on the electromagnetic principle. So as you can see, the biggest windmill generator on the world is located in Denmark. It is a type of V164. It has a height of 220 meters, and its blade is long as 80 meters. But as we mentioned before, we just want to power low grid electrical equipment. So we do not need so big size and so big energy. So what do we do? Here we introduce flow-induced vibrations. As you can see from pictures, it can be clearly seen that the structure has been aroused to shake dramatically in the wind or water flow, even at low wind speed. It is called so-called flow-induced vibrations. Flow-induced vibrations can be usually divided into four parts. For example, vortex-induced vibrations, galloping, flutter, and buffeting, also called weak galloping. So we can use, we must point that, usually speaking, FIVE should be treated as a harmful phenomenon that everyone wants to restrain. But here we can use it to generate power because it can efficiently transfer, you can say, flow energy into mechanical vibrational energy. Before we know what is FIVE, we must know what causes FIVE. As you can see from picture, Karman firstly planted this concept in 1911. It is called Karman vortex strait. When the flow passes the black body, in the behind it will generate periodical and alternative vortex shading strait. And this vortex shading strait can generate periodic aerodynamic force. Yeah, you can see that it can produce some aerodynamic force, comprise lift force and drag force on the black body. And here we must classify that. Usually in our research region, we called a black body with circular round, we call it cylinder. But if it is not circular, we call it prism. Okay, and as you can see, as action or driving force on the vortex shading strait, if we put the cylinder on a spring and add some damping on it, it will become a typical mass spinning damping system. And when the vortex shading frequency is getting very close to the natural frequency on the mass damping spin system, and it will be aroused to vibrate periodically, and then it is called vortex induced vibrations. Okay, now let's see what is the feature of VIVE. There often exist three branches in VIVE. Firstly, the initial branch. Secondly, the upper branch. And during the upper branch, one famous phenomenon can be observed. It's called lock-in, and then it will come to the lower branch. In the upper branch, there exists a special lock-in phenomenon that is caused by that if the wind speed is low, the black body does not vibrate. The amplitude is very small. But if the vortex shading frequency get higher with the increasing of the wind speed, the frequency, vortex shading frequency, if the frequency gets close to its natural frequency, and it will be locked on the natural frequency, they will be resonant. And during this stage, the vibration amplitude could be very large, very big. Okay. And when the wind speed gets more higher, what will happen? At this stage, the phase difference will get into a jumping point. That the direction of the movement will get opposite to the aerodynamic force. That means the vibration will be reduced, and the vortex shading will be enhanced. In this process, the energy has been transferred from the vibration into the into the vortex shading. But in this stage, in the initial stage, the energy can be absorbed to the mechanical vibration. So at the upper branch, you can see the amplitude is very good. And if we use this phenomenon as the energy harvesting, it is very good source. Okay, the first time of proposed energy harvester from vortex-induced vibration is planted by Professor Bonisas in University of Michigan at a conference. He first time presented the concept of vortex-induced vibration for adequate clean energy, also called FIVEH. And as it is reported, the first prototype of this is of the FIVEH has 3 cylinders, and it can power 4 homes per day. Okay, after that, I want to introduce some mechanism of VIV. Yeah, as you can see, like other problems in mechanical vibration, we also need to add some semi-empirical equations to describe this problem. Firstly, I would like to introduce this one. It is called weak oscillator model. It is presented by FIVEH at 2004. So this model treats the VIV as a kind of forced vibration. Why? Because they assumed that behind the cylinder there exists a weak oscillator, and this oscillator can give energy to the cylinder. It makes the cylinder vibrate, so it is treated as a forced vibration. And in the equations, how do we reflect it? The first governing equation is about the cylinder, about its moving, and the second equation is about its assumed weak oscillator. Here you can see that. But some other researchers, especially in the region of civil engineering, they think VIV is a kind of self-excited vibration. What does that mean? For example, they think what VIV is caused not only the vortex shielding, but it also depends on the aerodynamic damping. When aerodynamic damping enters a special value, and the system will get unstable, and it will enter the unpump bridge. Okay, and you can see from this picture, in this year, about in May, in China, a famous bridge called Humen Bridge has caused vortex-induced vibrations. But people don't know this bridge has been built for almost 25 years. So why in this time it will vibrate so seriously? That's because you look at this. They add some obstacles on the bridge this time, and these obstacles has changed the cross sections of the bridge. So it arrests the vortex vibrations of the bridge, and they just enter this region. Okay. Before the bridge is at this region, and now it enters this region. So you can see the amplitude is quite big. Okay. And okay, so we have comprehensively talked about the model of a system with one single cylinder. You can see that's only one single cylinder here. But what will happen if we put not only one black body? Professor FIVEH also proposed a model of 2 cylinders arranged tangibly. He thinks that the vortex shielding from the cylinder in the front can effectively influence the vibration of the second cylinder. So you can see from these equations there is interaction equation on the second cylinder. That means the first one also still acts as a single cylinder. It is controlled by these things, but the second one is controlled by both the weak oscillator model and the vortex shading effect, but it is red. In 2017, Professor AA found that when we put a cylinder behind the first vibration cylinder, what we will find? We find that it will be significantly infected by the interfield cylinder. So you can see, firstly, it was typical VIV, but it enters limit cycle oscillation here. So it becomes scalloping. It is unstable. Okay. So it proved that this model is not quite accurate because it does not consider the influence of the second cylinder on the first cylinder when their distance is close. So what do we do? So it is not easy to model something like this. Okay, so what can we do to accurately build a governing equation to model such a VIV problem? So we can use CFD. CFD technology is very good at solve these such problems. Okay, in CFD there are some important points. Firstly, we must justify whether it is laminar or it is turbulence. So in this region, someone thinks the judgment point is whether the Reynolds numbers is upon or below 180. But someone says the number was 500. Not sure. Okay, and there are quantities of CFD technology, but the most common used can be divided into I think two types. Firstly, the finite volume method, and the second lattice Boltzmann method. Okay. And about the turbulence solving, we can use some, for example, large AD simulation, Reynolds average Navier-Stokes, direct numeric solution. So when we talk about Reynolds numbers, because Reynolds numbers is a very, very important number in a CFD study. If it is higher than 180, so commonly a three-dimensional simulation should be conducted. So, but if you just want to get the lift force or the vibrational amplitude of the cylinder, a two-dimensional simulation is also, I think, is enough. But if you want to accurate to get a phase or something like some other things, I think 3D simulation is important. Okay. So why we use CFD? From this picture, you can see that this picture is a typical example of simple vortex induced vibration. And you can see that there exists a pair vortex shadings in a single period. And it is interesting that you can see the color. The blue color presents its rotation. The vortex shading rotation is negative, and the red color presents that the rotation direction of the vortex shading is positive. And you can also get the vortex vectors from this picture. Yes, so it is very it is very real from I would say, but not only some easy equations. Okay. Okay, so here let me introduce some of our recent works. So we used the software Flint it is a good technology called overlap grid. What does it mean? So the green one is the ordinal grid. So if we compute a flow-induced vibration problem, we must meet the problem of the grid or the mesh distortions. The mesh will easily be broken, and the simulation will be stopped. But here we use a new overlap grid. That means we put another grid on this hole, and it can transfer some data from the vibrations and the flows. So we no longer need to solve the moving grid to have some mesh distortions. So here it is some flow chart, working flow chart. So as you can see, firstly, we can generate some raw grid and start to assemble grid. So we dig holes, that means we dig holes here, and then we optimize the whole surface. Then we can establish, for example, this red grid. It is called overset grid, and transfer back to the assemble grid. And then we set boundary conditions to, and then we can simulate. At last, we need to judgment if it is convergence. If it is convergence, we can stop the simulation, and the simulation is finished. We can get what we want. Okay, so this picture shows that we can get very good nice result. For example, such problem, it is round, it is circular cylinder with two rods or some other attachments, and get the developing process comprehensively from the CFD. Firstly, we can get at a lower flow speed. It is a simple 2S patterns. That means 2S. That means one period with two different vortex shading. And as it develops more, it will develop with more typical 2S. But if we still enhance the flow speed, we can find that it will become into a P plus S pattern, and the vibration amplitude will get higher and higher. So I think it is good at solving such problems. Okay, that this example is containing only one cylinder. If we put in multiple cylinders, what will happen? So as we mentioned before, CFD technology is very good at solve such problems. Here we also add the overlap grid into here to solve the yellow energy harvest. The yellow one is the energy harvest. So we can also get comprehensively with the vortex shading processes. Okay, this picture we see is a comparison of finite volume method and lattice Boltzmann. So as we mentioned before, from this picture there exist different colors. The blue color is represents the negative direction of the vortex shading, and while the red color represents the positive vortex shading process. And here you can see if we use the lattice Boltzmann method, we can get that. So firstly, we do not need a high grid. It is no grid platform. It just have lattice. Lattice is, I think this is good at solve some very hard computations. For example, so usually this is a flowchart of the LBM method. Okay, firstly we need to input some parameters and to do some initialize, and then we must calculate this equilibrium distribution function. So this function is some like Navier-Stokes equation in CFD in FIVEH. This is something they are similar, and they will then we will compute the particle calculation, regression, and the boundary processing, and last we calculate the macroscopic quantities. That means the velocity, and the oscillator velocity. So at last we judge whether it converged, and then to judge whether the computation will be stopped. There are two common models of IBM. For two-dimensional simulation, we usually use D2Q9 model, and for three-dimensional computation, we usually use D3Q27 model. Okay, this is typical example. We use the LBM to solve the flow patterns of our vortex-induced vibration cylinder with Y-shaped attachments. As you can see, without the attachments, so the green one represents a smooth cylinder. This picture presents it is in the lock-in phenomenon. So the vibration amplitude is a little big. So the maximum is 1.8 d. But if we enhance the wind speed, as we mentioned before, for VIV it has a lower bridge, so the vibration will be suppressed, and the amplitude will be reduced into 0.3 d. But if we add the Y-shaped attachments on this, what will happen? So as you can see, in lower speed, so the vibration amplitude is only 1 d, still lower than this one. But if we enhance into a higher wind speed, the vibration will get very strong, and the maximum vibration amplitude will get into 6 d. So it's a very benefit for energy harvesting. Okay, this is our recent work. We want to comprehensively study the lift and drag aerodynamic response near the square prism. So our target is to comprehensively solve its the aerodynamic force with the different incoming wind attack angles. And furthermore, we can get some coefficients, for example, galloping efficiency, and to accurate to simulate it. So we found that for three-dimensional simulation, the result is more is really better than is very close to the experiments. Okay, these pictures show some designs of where we energy harvesters. For example, this researcher has put a split plate behind the black body to induce galloping, and this man has used 2 degrees of freedom where we energy harvesting. And this one, these people has used combined by magnet and piezo. There's so it is the piezo energy harvester combined with the magnetic. Okay, let's summarize what is the benefits of VIV energy harvesters. Firstly, it's because it has a typical lock-in phenomenon. So it has also performance high voltage output in the lock-in phenomenon in the special wind speed region. And secondly, we can absolutely design such energy harvests into a very small size, so it can be worked individually. We do not need to apply them in grid. So that means we can use it at our home or take it with us. And at last, I think it's very, very important that for VLV and harvesting, because it has a low branch, so if the wind speed is quite strong, so the vibration will be suppressed. That means if the wind speed is quite strong, the system can protect itself. It will not damage even the wind speed is quite big. Okay. Okay. After talking about VLV, I would like to introduce the galloping. As you can see, galloping is a velocity dependent damping controlled instability. So this picture is very, very easy to let people know what is galloping. So imagine this is a wire line. So firstly, the cross sections is a round shaped cross sections. So it will happen typical VLV, where what is this vibration. And why we see that? Because the direction of the movement, or see the velocity, is always opposite to the aerodynamic force. That means when you move down, you can inverse the aerodynamic force to up direction. It will stop you getting very strong. But if the wire is coated with some, for example, ice or rainwater, the cross sections has been changed into some like this shape. So what will happen? So it will be happen that the direction of the velocity is the same as the aerodynamic force. So what does that mean? That means if you move forward, and someone has pushed you to move, so the movement will be stronger and stronger. So as you can see, the system will be damaged. So here we must clarify that galloping is a type of limit cycle oscillation, because it is related to its linear and nonlinear dynamic damping. The nonlinear dynamic damping makes the amplitude at a certain wind speed will not get unlimited high. It will get to a certain value. Okay, this is just we talked. This is designed by Professor A. And this is the aerodynamic force. It contains generally two parts. Firstly, the linear part, and secondly, the nonlinear part. The linear part can dissolve when it can happen, when the galloping happens, and what is the maximum value of the amplitude. Okay. So let's summarize. What is the benefit of galloping and harvesters. So it is a low frequency and high amplitude oscillates. That means we want high power. If we want very high power value, we can use galloping. And the amplitude increase with increase of wind speed. So it is compared with VLV. There are two different types of flow-induced vibrations. Okay, so we did some experiments to investigate if we put the attachments on the smooth cylinders, what will happen? We will see that galloping will be aroused. Okay, But if we take off the attachments, it will becomes back to VIV. That means if we designed such energy harvester, if the wind speed is low, we can get down the attachments. If wind speed is quite high, we can get on the attachments to harvest the different wind speed energy. Okay, so then we did some other studies to further develop the energy harvesting performance. For example, we have added some magnets to make the system become too steady. Yeah, too steady, and by using this configuration, what we found that the second beam, this is second beam. The second beam firstly without the magnets, so it can only work at about 2.4 millimeters, and if we use the magnets, we can find that the cutting speed will get down to 1.9. This is very good for enhancing the performance of energy harvesting. Okay, this picture comprehensively showed why this phenomenon can be seen. You see, when the wind speed is low, it can only vibration at its first potential well. Okay, so just between here. Okay, so it's called intro well response. So the response is always positive or always negative. But from this you can see for second beam, some little chotic has begun. But if you enhance the wind speed, that means you add more wind energy to the system. So the vibration will get to another potential well. So it will break the first potential well, and it has two equilibrium points, right? So the amplitude is sometimes positive and sometimes negative. Okay, then and after this, we have imagined that what will happen if we want to conjunct the VIV and the galloping, because for simple VIV there always is a round shaped cross sections, and for typical galloping it is always a square prism. So we combined the black body into this shape and comprehensively did a parametric study to this, and unfortunately we found that such shape of black body can efficiently reduce enhance the performance at the traditional wind stage. That means you can see this red line, okay. And we have did some other works. For example, in 2015, Dr. Li Huatang has presented the equilibrated circuit study of galloping energy harvester. That means we saw this. We use this. So so this function is very normal in energy harvesting from fluid-induced vibrations. But the hard point is that we often treat it as a simple resistance. We only treat it as AC. But if we use a DC, this function equation is impossible to solve. So we use this method to solve this problem. So we can solve this not just AC, but we can solve DC and some other type of circular, for example, SSHI, SCE. So we can also get this solved. So this year we have solved this lack. So Dr. Tang has solved the galloping aerodynamic model. So we have because as we mentioned before, the Ricker oscillator has two Gaussian motion equations. It's very hard to plant it into an equivalent form. So we used another model to plant the aerodynamic force into equivalent circuit form. So we get the vortex VRV energy harvesting by this method. Okay. Okay, and we have did some other studies. For example, we have studied the position influence on the two energy galloping energy harvesters, and we solved different incoming wind speed into energy harvesters to so this design can harvest any wind directions energy. Okay, and Zhao Liya has stopped this combined. She combined galloping vibration energy harvester with normal basic excitations. Okay, next, some application examples of fluid-induced vibration energy harvester will be introduced. This company about in 2014, it firstly in Spain it is a Spanish company. So it firstly designed vortex bladeless and wind turbine. So as you can see, it's bladeless. So he used the principle of vortex-induced vibration, right? This is maybe the first time I see someone to build production out by using fluid-induced vibrations. And this one is is the BPS company Australia. They designed they designed the fish-like biostream. It calls biostream. Yeah, to harvest the water seed, to harvest the water energy. And this one is to be designed to harvest the tide energy in the offshore. Okay, and this one is designed to as a self-powered temperature management system by using piezo plug. So I think there still exist some challenges in this fluid-induced energy harvesting studies. Firstly is about the series. The series of FIVEH energy harvesting is still not complete. And the flow field is very, very complex, especially when it comes to turbulence problems. It should be further studied. And secondly, I think almost everyone concerns about is the efficiency of energy harvesting. But to tell the truth, I don't think efficiency is very important because we just need to power some very, very low power grid equipments. And we just need to power low grid and sustainable, and we just not need to change batteries. So I don't think efficiency is quite good, quite important. But if we can find some ways to enhance efficiency, it is very, very nice thing to improve this energy harvesting performance, and we can design some more and more prototypes to make it as a production or some other things. And lastly, it's cost. The cost is very still I think is very high for me because I usually use piezoelectric energy harvesting. So the piezo sheet is it's very expensive. For MFC it's about 100 European for one. So the cost is still high. So I'd like to make a conclusion of my presentation. So harvesting energy from ambient environment has a very good perspective because the energy is clean, endless, and unstoppable. So FIVs are also good medium to transfer flow energy into mechanical vibratory energy because the redness phenomenon. And we can use some technology to enhance or to combine the energy harvesting from FIV. For example, non-nano technologies, intelligent regulating elements, the hybrid energy harvestings, some new materials, and to combine the wave energy harvesting. Because the wave energy is every time, it always exists. And at last, I think nowadays it's very popular in USA and in China. Many researchers have become use artificial intelligence, for example, machine learning, deep learning, to get the relationship between some fantastic phenomena. Okay, thank you for the National Science Foundation of China. And this is some collaborators, Professor Zhou Shenxi, Tang Lihua, Zhao Liya, Yang Kai, Professor Daniel, Professor Li Tak, Professor Hu Guobiao, Zhu Hongjun, and this is my graduate students. Okay, my presentation is over.
Okay, thank you very much.